Welcome to the Henry AI Labs walkthrough of Keras code examples. Keras has provided 56 code examples implementing popular ideas in deep learning. This ranges from the basics such as simple MNIST and IMDb text classification, all the way to cutting-edge research ideas such as knowledge distillation, supervised contrastive learning, and transformers. We'll also explore fun generative examples like variational autoencoders and CycleGAN. My contribution to these code examples is to explain every single line of code in each of them, walking through each of the individual Keras examples. I'm not the author of these code examples. Please consider starring the GitHub repositories to show support to the original authors. This Keras example will show you how to use the vision transformer for image classification. Transformers have completely taken over natural language processing, and now we're starting to see them integrated into computer vision tasks as well, like image classification, object detection, semantic segmentation, and so on. This video will show you how to implement the vision transformer that has the Google, the 16x16 image patches is all you need paper, where particularly the way they split up the image for input to a transformer is they're going to split it up into these n by n patches and then flatten this as a sequence and then treat each of these patches as a token, similar to as if you had a natural language processing transformer that would treat this as implement the patch encoding layer. They're going to split this into patches and treat these patches as tokens. There have been a few ways of integrating transformers into computer vision, things like the data efficient image transformer or the botnet. This one is the vision transformer from Google, made famous in this paper. An image is worth 16x16 words, transformers for image recognition at scale. So from Google's AI blog post, this GIF really illustrates how this is going to work. So we take our original image and we're going to divide it into patches. These patches could be 6x6, 16x16, whatever. This is a hyperparameter of the algorithm, whatever best splits this up and has the best downstream performance. So then we're going to take these patches and we're going to flatten them out into a sequence and pass this into our transformer layer. So we're also similar to transformers use a position embedding where you would tell the transformer something about the left to right ordering of a text sequence, and in the case of the vision transformer, we're going to provide these embeddings that tell the transformer where in the original image each patch was sourced from, and then we're going to add this embedding to our original patches and then pass it in through the transformer encoder or decoder layer, and then it's all the same. It could be like a GPT, a BERT, any kind of transformer architecture is compatible with this kind of input representation. So similar to BERT, we're going to slice on the CLS token, add a multi-layer perceptron classification layer, and then a softmax that is going to do our image classification task. In this case, we're going to experiment with CFAR10 and CFAR100. The first thing to note in the tutorial is to install the TensorFlow Add-Ons package into Google Colab. So you do this by doing shell command pip install TensorFlow Add-Ons. TensorFlow add-ons, as stated in this documentation, are little functionalities in TensorFlow that haven't been completely integrated into core TensorFlow and are mostly community contributions. And in this case, what we're using is the Atom W optimizer. So if you use the Hugging Face transformers, you know that this optimizer is very popular. I don't know exactly the literature about why exactly they use this, but I just imagine that it works better than, say, stochastic gradient descent, or I guess just atom without weight decay. So particularly we're going to be importing this optimizer for training our vision transformer in this code example. The tutorial continues with our pretty standard imports: NumPy, TensorFlow, Keras layers, and then our TensorFlow add-ons library. Then we're going to download the CFAR100 dataset. So differently from CFAR10, CFAR100 has 100 classes. So 100 is the cardinality for our Y labels. We have 100 different object categories, and it's the same size. We still have 50,000 images. They've just been labeled more fine-grained. And then we have the same thing with our test set, 100 labels as well, 10,000 test images. So now we see the hyperparameters of the vision transformer. We have the learning rate, the weight decay that's used in that Atom W optimizer thing. We have our batch size, number of epochs, and then we have the kind of the hyperparameters for the actual transformer. So the first of which is the image size. So we're going to blow up these CFAR10 32x32 images to 72x72 just using a pre-processing resizing operation. This is something like say bilinear interpolation, which is used in like just a super resolution technique without any deep neural networks, just where you have like a kernel filter that averages out the pixels to upsample an image. And then the patch size of 6 is going to be the size of these patches as we're dividing up the image. So we're going to be taking 6x6 patches and splitting this into a grid. So our original 72x72 image is going to turn into a grid of 6x6 crops of that original image. From the image size and the patch size, the next thing to do is to store the number of patches in a variable that we'll be using when we're defining the position embedding. So from this hyperparameter of the image size and then the number of patches, so we know that we're going to be sliding across a window that's taking 6 by 6 patches of the image, we can calculate how many patches will be left in the resulting image. And we need to have this information for when we're defining this position embedding. So transformers are famously set operations, the attention layers. They don't have any sense of the original sequence ordering of a model. So to bias the attention layers, we add this prior of the position embedding. In natural language processing, it's common to have this left to right position embedding, and in the vision transformer, we're going to add an embedding for where in the original image this patch was sourced from, as stated in this 1, 2, 3, 4, 5, 6, 7, 8, 9 thing in this Google AI Lab example. The following lines of code define the hyperparameters for the vision transformer model itself. The first of which is the size of the hidden dimension feature vectors in our model. We have 64 dimensional vectors as the projection dimension to project these patches into these 64 dimensional feature vectors that are then concatenated together as input into the first transformer encoder layer. So this is describing the hidden dimension as we take these patches and then transform them into feature vectors. The next hyperparameter is we have 4 attention heads. So in multi-head self-attention, this describes having 4 different parameterizations of the query key and value matrices. So we have 4 separate transformations that then aggregate the outputs of these 4 separate self-attention parameterizations from the previous layer as you go from, say, layer L to layer L plus 1 with these self-attention layers. The next of which is the transformer units list. We're going to be overwriting the multi-layer perceptron layer to add a skip connection like the ResNet. In the transformer blocks, you have a skip connection from the output of self-attention, and then it goes through a feed-forward layer that's going to compress the dimensionality, and then you skip ahead with the previous output from the previous dense layer. So this is the parameterization of these skip connections in the transformer blocks. So then we say we have 8 transformer layers. This describes stacking on top of the transformer encoder block, just repeating it 8 times, and then we have the hidden dimension of our multi-layer perceptron layers. Next, we're going to apply some data augmentation to prevent overfitting with the CFAR 100 dataset. We have a normalization layer that's going to normalize the pixel values in the CFAR 100 images around a given mean and standard deviation, and we're going to calculate this mean and standard deviation from the dataset by using this data augmentation.layer0.adapt xtrain. So this is going to be fitting the normalization parameters with the CFAR 100 dataset. Then we're going to resize the images from 32 by 32 up to 72 by 72. Then we add horizontal flipping, random rotation, and random zooming. So this is our data augmentation layer as we originally take a 32 by 32 image, blow it up to 72 by 72, and then add some other transformations to it as well. Mentioned previously, we're going to be overwriting the dense layer to add a skip connection. So rather than using model.add dense, we're going to be overwriting this with a custom multi-layer perceptron layer that we're adding with this functional API, passing in this x is the argument, x is the argument. This is the Keras functional API for defining these custom layers. So what we're doing here is we're adding a skip connection. We have our list as we're looping through the hidden units, so we know exactly how many hidden nodes to use to transform the dimensions so that they are compatible with each other on the output of the skip connection and the output of, say, the features from layer L plus 1 as we're adding in the skip connection to bring the features from layer L to layer L plus 1. So we have this custom layer. We have the dense units, and we have a dropout hyperparameter as well to normalize the contribution of these features. The following lines of code are going to overwrite the Keras layer object to implement this patches layer. This is going to be the layer where we're taking in a 72 by 72 image and then transforming it into a grid of these, in this case, 6 by 6 patches. That's a hyperparameter that you can control. You could change it to 16 by 16, 32 by 32, whatever patch size that you're trying to use. So what we're going to be doing is we take in the image. The way that we overwrite the Keras layers is we start by initializing the layer by inheriting the super initializer with the Keras layers.layer, passing in the new argument, the new name of our class is the argument, and then we're going to have a state variable of patch size. So the patch size is going to be the key variable throughout applying this transformation to the image. So then when we overwrite the call layer, this is what happens as you do a forward pass through this layer. We start off by getting the batch size from the input, which is our batch of images, not just a single image, but an entire batch of images. We do this by indexing the tf.shape tensor on the 0 column. And then we're going to use, so surprisingly, this functionality of extracting patches is already built into tf.image. Probably it was originally developed as a data augmentation technique. Things like the jigsaw augmentation that's really popular in self-supervised learning also does this kind of splitting up the image and then rearranging these patches. So it probably comes from that. But we already have tf.image.extract patches. We just pass in the images. We pass in the sizes of the patches that we're after. And then we have the stride length. So the stride length is describing whether we want to have these patches be overlapping or not. So we could imagine having, say, a stride length of 2, and then these 6x6 patches would be overlapping with each other rather than completely disjoint as you traversed from the left to right, top to bottom of the images. So then we just have rates, padding, centered hyperparameters with this traversal as we slide this window across and patch up the image. Then we finally return the patch dimensions, and then we reshape the image batch so that now instead of just being the number of images, the height by width, we now have the number of patches, and then we reshape it to what it was, which is the batch size and then the patch dimensions. And I'm not sure exactly what this -1 is doing, but basically what we're doing is we're reshaping the size of this tensor because now it's a different kind of object. Now it's a sequence object compared to just this kind of static height by width by RGB image object. This next block of code is going to let us visualize these patches with matplotlib. So what we have to do here differently from just a regular plt.im show is we're going to have to loop through these patches and then plot them and have them occupy a space in the plt.subplots indexing. So we first define the plt.subplots by doing ax equals plt.subplot n I+1. I+1 is how we're traversing the index position of our patches and then also indexing the plt.subplots. And we're just going to be reshaping the TensorFlow patch to get just the individual patch, and then we just plot it on our axis. So now we see the difference between an original 72 by 72 image and now the grid of patches that we're going to be inputting to our vision transformer model. And we also get the hyperparameter reported here, the patches per image. As we have a 72 by 72 image and we slide a 6 by 6 kernel across it, we end up with 144 patches. And then we have 108 elements per patch, which is just 6 by 6 by 3. So 36 times 3 is 108. So this is how many values are in each of these patches, because this isn't just a 6 by 6 grayscale patch, it's still red, green, blue on the channel axis. Here's another really important detail of implementing the vision transformer to note. This is implementing the patch encoder. So as previously stated with this GIF animation from the Google AI Lab blog, we're going to be having these we have these projections of the patches, and then we're going to be adding a learnable embedding for the position. So this is used in natural language processing and any kind of transformer architecture because transformers are set operations. They don't have any sense of the original ordering of the sequence as they process it with this matrix multiplication and then the softmax operation. It doesn't have a prior knowledge on the original structure of where the sequence of tokens was sourced from. In our case, left to right, top to bottom image patches. So we're going to be learning this embedding as well. That's another important thing. The original Transformers All You Need paper uses a fixed embedding where you add this sine wave or this cosine wave rather than learning the embedding. Learning the embedding is similar to ideas like word embeddings, where we have a table that indexes a vector that represents each of these discrete encodings or like categorical codes. So in our case, we originally have 144 position embeddings because we have 144 patches, and each one of these represents like a discrete object of 0, 1, 2, 3 up to 144. So we're going to be mapping this into an embedding table that transforms that 0, 1, 2 into a vector of the same projection dimension as we're transforming our patches so that they're compatible to be added to each other. So the 0, 1, 2, 3 shown in this animation, they have to be 64-dimensional vectors as well so that you can add them to the projection of the image patches. So that's what we're doing in this layer. We define the number of patches, we add a dense layer to the projection, and then we have this layers.embedding. This is how in Keras you define one of these embedding tables that takes from an index code into a position in an embedding table and returns this vector. So then when we call it, we pass in the parameter on the number of patches, and then it defines this embedding layer, and we add together the projection, which is the layers.dense. This is the output from the transformation of the pixel grid, and then we're adding this with our embedding. Having defined custom Keras layers to do the patching and then the patch embedding, we're now ready to put this all together into the vision transformer architecture. So as stated in the text under the build the ViT model, we have these multi-head attention blocks. We're going to be stacking them together by using the syntax of for and then just placeholder in range the transformer layers hyperparameter from earlier. We're going to be looping through this Keras sequential API or functional API where we pass in this x1 over and over again, x3, x2, x3, 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 x2, and then we just loop through it again, and it has the encoded patches namespace from this previous output as we can now come to say transformer layer 2, 3, and so on. So what we're doing is we're pretty straightforward. The transformer blocks, they have this intermediate dimension of similar to a natural language processing kind of sequence modeling. It has the number of patches by the projection dimension. These are these the intermediate matrices, the intermediate feature vectors of this model, and we're going to be indexing, similar to BERT, the CLS token, the leftmost position in this matrix. So this matrix, it has the width of the number of patches, and then it has the height of the projection dimension in this matrix right here, ignoring the tensor shape, which is the batch size. But we have this matrix of number of patches and then projection dimension, and we're going to be indexing the leftmost position to add this multi-layer perceptron head to the classification of the image classification task of CFAR 100. So all we do is we take in the inputs. This is our original 32 by 32 image. Then we add our data augmentation layer. Also worth noting, when you have this kind of syntax where you put the augmentation layer as a part of the model, the data augmentation is going to happen on the GPU, not on the CPU pre-processing it. It's going to be augmenting the data on the GPU, which can be advantageous with the parallelization for things like rotation, translation, and so on. Those are also gigantic matrix multiplications that benefit from living on the GPU. So then we're going to create the patches, as mentioned previously, split it into this grid of patches, add in the embedding layer, add in our loop of transformer layers where we have things like our custom multi-layer perceptron head to add the skip connection. And you see we have the add where we have the x3, x2, and so on. So layer normalization, that's another big part of these transformer blocks. And then finally, we take the output, which we're calling our representation. We flatten it into a vector, add a dropout, add multi-layer perceptron again. And then we have our final classification into the number of classes as we're repurposing this transformer for image classification with 100 outputs. Another detail of this that I wasn't able to really understand is how they have this outputs equals logits and then sparse categorical cross entropy from logits equals true. So the way that I'm interpreting this is that there's no explicit softmax activation layer, and rather they're doing something directly from the logits, but I'm not exactly sure how this works. Maybe someone in the comments would know exactly how this works, but so sorry that I can't explain this. So then what we're doing is we're compiling this together into our experiment. So we start off with that atom with weight decay optimizer that we're getting from the TensorFlow Add-Ons. We add our hyperparameters, learning rate, weight decay. Then we're going to compile the model with the optimizer, this loss function we just talked about, and then we have the metrics that we're going to be reporting in our callbacks. We have the categorical accuracy and then the top K categorical accuracy. So it's common in things like ImageNet, or in this case we have CFAR 100. So similar to applications like information retrieval, we have a massive set of potential class labels. We have 100 class labels. So it's also useful as a proxy to see how our model is doing, to see how well it's performing. Even when it's incorrect, how well does it guess? Is it at least within the top 5? So if it's a deer image and is classifying it as a horse, at least the deer is still in the top 5 predictions. And that gives you more information about the performance with something like these high cardinality class label classification problems. So now we have the checkpoint file path. This is in our model checkpoint. We're going to be saving the model weights. It's similar to things like early stopping and all this hyperparameter stuff. It's really important to have an understanding of this checkpoint file path and saving and restoring the state of the training in the model weights. When we're doing things like large-scale hyperparameter optimization or any kind of large-scale experiment needs to have some kind of system like this. So then we just pass in the training data, the X's and the Y's, batch size, epochs, our validation split, and then our checkpoint callback to save the weights. When it save best only means if the performance is going to exceed the previous best on the validation set, then that just tells the callback to save those weights to our checkpoint. So then when we're finished, we're going to load the weights from the file path, and then we're going to evaluate it by doing model.evaluate, and then we're going to just return this, and we return the history. History is this object that you can use to plot the training and validation curves throughout training. So then with all that defined, we just define the ViT classifier, and then we store this history object in the run experiment. This is the output, the training and the validation curves throughout training. And then because we don't have our verbose hyperparameter on, a verbose parameter on the model.fit, we see these outputs throughout training, and we see on the GPU from Google Colab. This takes about 45 seconds per epoch. So running 100 epochs takes roughly about an hour. Here we are at the end of training 100 epochs with this vision transformer architecture. We end up with about 55% test accuracy and about 81% top 5 accuracy. And we see some overfitting because we have achieved 78% accuracy, 96% top 5 on the training set, but then we have this train test difference between the accuracy drops off by about 24%. So this could maybe be alleviated with more data augmentation, more regularization. The author of the notebook notes that ResNet 50 version 2 trained from scratch would achieve 67% accuracy. So this vision transformer implementation right off the shelf, it isn't better than the state of the art, or ResNet is like one of the efficient net is probably more the state of the art, but it is not better than these convolutional neural networks right off the bat. But the author at the end denotes things like In the Google paper, they pre-trained the ViT model with the JFT 300 million dataset. These transformer neural networks in natural language processing, they are pre-trained by doing language modeling on these enormous data sets like all of Wikipedia or like a stack of 100,000 books in the books corpus and things like that. So it's looking like the vision transformers tend to benefit more from scale of data in the pre-training phase. Maybe that can be simulated with data augmentation and improve the performance of this model. Also these hyperparameters like not just the learning rate schedule and data augmentation stuff, but also just the design, the number of layers, the input dimensions, the patch size of these as we split this into the grid, and all this kind of stuff can heavily impact the performance. So Vision Transformer, it's still a really relatively new cutting edge idea, is bringing these transformers to computer vision, image classification, object detection, and so on. So really exciting. With this notebook, you now have an implementation of Vision Transformer, and you can start figuring out how to close this gap between the Vision Transformer and the ResNet 50 version 2 or other kind of convolutional networks like, say, EfficientNet. So to recap, some of the most important things from this notebook, I think, are knowing how to overwrite this Keras layers to implement the patching, how to implement this patch encoding layer with this embedding, and then seeing how it all fits together by looping through the attention layers, adding in the data augmentation, resizing the image, the patches, the patch embeddings, and then passing it in for the output for image classification with this Vision Transformer model. So thanks for watching, and I really hope this helps you to do some experiments with the Vision Transformer and figure out how to improve the state of computer vision and image classification with this really exciting new Vision Transformer architecture. And also I hope it inspires inspiration into exploring other ideas like the botnet, which is kind of a hybrid between ResNets and Vision Transformers, or maybe the data efficient image transformer. There are a lot of new ideas on how to exactly bring this transformer architecture into computer vision, things like CFAR 10-100 or ImageNet. So thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos, and please check out the rest of the Keras Code Examples playlist.